Hi, Ollie here. Thank you for checking out our work on multi-camera trajectory forecasting, or MCTF for short. Predicting the future trajectory of an object is a commonly explored task and has a wide range of applications from autonomous driving to video surveillance. Many excellent existing models such as Social LSTM, SOFI, and Social GAN successfully tackle this task, which we term single-camera trajectory forecasting. As shown here in red, this task looks at predicting a future object trajectory in the same camera in which it is observed. In our work, we introduce the task of multi-camera trajectory forecasting, where an object trajectory is predicted across multiple camera views. This formulation introduces new challenges, such as identifying which camera a person will reappear and when they will reappear. Herein, we consider predicting the trajectory of humans, although MCTF can easily be generalized to any moving object, such as vehicles or animals. Our contributions are as follows. We introduce the MCTF task, we release the Warwick NTU multi-camera forecasting dataset, and we present several baseline approaches for predicting the next camera a person will appear in our dataset. Let's take a look at the WNMF dataset. We gather footage on the NTU campus in Singapore as shown here. Notice that the faces in the dataset have been blurred to preserve the privacy of those captured. We use the retina face model to perform this blurring automatically. The camera network topology is shown here on the left. There are a total of 15 cameras. We record footage over 20 days in 20-minute chunks, from 8:30 am to 7:30 pm. We collect a total of 600 hours worth of footage. Annotating data suitable for MCTF is a laborious task. We must first annotate each object trajectory in each camera view, and then associate these trajectories across camera views. Fully manual annotation of a dataset at such scale is infeasible, so we take a semi-supervised approach. Given footage from C cameras, we run pedestrian detection and tracking algorithms, resulting in tracks for each camera view. We use the Mascar CNN detection and deep sort tracking algorithm. We then flag entrance and departure tracklets. We define an entrance as the first 20 frames of a track, and a departure is similarly defined as the last 20 frames of a track. Next, we search for cross-camera matches and manually verify that these proposed matches are correct. We use 3 criteria to find cross-camera matches. To be a proposed match, 2 tracklets must have similar appearance features. These are computed using an off-the-shelf person re-ID model. Both occur within a time window of 12 seconds. And occur in different camera views. The human annotator then verifies if the pair is the same individual for the pairs that meet all the criteria. This step assures data quality at all stages, as the annotator also discards poorly localized detections and fragmented tracks. Here is an example departure-entrance pair found using our labeling procedure. Here we see the departure of an individual from camera 9 and the entrance in camera 10. By referring to the network topology, we can see that these 2 cameras are situated next to each other. We verify 2.3 thousand such pairs. With our data release, we provide these matched pairs and pre-computed tracking information. Using our newly collected dataset, we consider a straightforward formulation of the MCTF task, predicting the next camera of reappearance. Given an observed trajectory in one camera view, our goal is to predict the next camera this individual will reappear. This work explores this classification problem, though we provide full trajectory information so future works may investigate more fine-grained trajectory prediction. We implement 7 methods for this task. The first 3 methods use simple heuristics. The next method uses handcrafted features. The final 3 methods use neural networks to learn features directly from trajectories. Here we show the top 1 and top 3 classification accuracy for the 7 methods. We observe that the neural network-based approaches consistently outperform other methods, although there is no considerable improvement in using recurrent models over a fully connected network. To summarize, single-camera trajectory forecasting has seen considerable attention from the research community in recent years. Our work is the first to consider trajectory forecasting in a multi-camera scenario. We have collected the WNMF dataset for MCTF. The dataset is available at the GitHub link below. We present several baseline methods for predicting the next camera of observation on the WNMF dataset. This work is a collaboration between the SIP lab at the University of Warwick, England, and the Rose lab at the Nanyang Technological University, Singapore. Thank you for your attention. We look forward to seeing future works on MCTF.